Okay, so now moving on to section 5.6, which is actually just everything we've already done, but just kind of bringing it all together. So it's more practice of finding maximums, minimums, inflection points, graphing, intercepts, domain, range, all that fun stuff. So first example, I want you to go through number 1 on your practice packet. Pause the video, unpause when you're ready to check your work. Alright, so number 1, our final graph should look like this. Now let's look at some of those key points. So we'll go back up to the top here. Okay, so this is a polynomial function. Hopefully we recognize that. I was nice enough to have it factored for you as well. The domain is all real numbers. The x-intercepts, since it's factored, it's pretty easy to get those. We get negative 1, 0 and 2, 0. The y-intercept is 0, 4. The first derivative is 3x squared minus 6x, and the second derivative is 6x minus 6. Now we want to find our critical values. So I set the first derivative equal to 0. I factored out a 3x. Set each factor equal to 0. I get x equals 0 and x equals 2 are my critical values. Now I give you the choice, either do the second derivative test or the increasing and decreasing chart. So here is the increasing and decreasing chart. Here is the second derivative test. In this case, I chose to answer the question using the second derivative test. But again, the increasing decreasing chart tells us the same information. So since f prime of 0 is 0 and f double prime of 0 is less than 0, the point 0, 4 is a relative maximum. So relative max is 0, 4. Since f prime of 2 is 0 and f double prime of 2 is greater than 0, the point 2, 0 is a relative minimum. So 2, 0 is my relative min. Now we want to find possible points of inflection. So I set the second derivative equal to 0 and I solve for x and I get x equals 1. So my possible point of inflection is at x equals 1. So I use my increasing decreasing chart for the second derivative. And I see that I have a change in sign, so I have a change in concavity. So now using my derivative speak again, since if f double prime of x is less than 0 on the interval negative infinity to 1, and f double prime of x is greater than 0 on the interval 1 to infinity, the point 1, 2 is an inflection point. So my inflection point is at 1, 2. There is no vertical asymptote, there is no horizontal asymptote because it's a polynomial, but the end behavior is down, left, up, right. And I know that, remember, the degree is odd, the leading coefficient is positive. So that's how I know my end behavior is down, left, up, right. So now I can plot my intercepts, my maximum and my minimum and my inflection point, and using my end behavior I can get an idea of what the graph looks like. Alright, next one. Pause the video, answer all of these or solve, do all the curve sketching, and unpause when you're ready to check your work. Alright, here for number 2, our function should look something like this. Here's our minimum, inflection point, and just an intercept. So how do we get those? Okay, again, this is a polynomial, so the domain is all real numbers. It's relatively simple to factor, so my x-intercepts are 0, 0, and negative 2, 0. My y-intercept is also 0, 0. The first derivative is 12x cubed plus 18x squared. The second derivative is 36x squared plus 36x. Finding my critical values, I set the first derivative equal to 0. I factored out a 6x squared, set both factors equal to 0, and I get critical values of x equals 0 and x equals negative 3 halves. So for this one, I chose just to do the increasing and decreasing chart, since last time I used the second derivative test primarily. So I did an increasing and decreasing chart. I see that it changes sign between or around the negative 3 halves, but it does not around the 0. So since f prime of x is less than 0 on negative 3 halves, or I'm sorry, on negative infinity to negative 3 halves, and f prime of x is greater than 0 on negative 3 halves to 0, the point, negative 3 halves, negative 81/16, is a relative minimum. There is no relative maximum. One thing I want to point out real quick, so in using my derivative speak, notice that I just used the interval negative 3 halves to 0. I did not say negative 3 halves to infinity, although it is positive greater than 0 also, because at 0 it is not greater than 0. At 0 it equals 0. So I want to make sure to restrict my interval still. All right, so then I have here is my relative minimum. My relative maximum is none. Find possible points of inflection, so I set the second derivative equal to 0. I factored out 36x. I set both factors equal to 0, and I get x equals 0 and x equals -1 as my possible inflection points. So then I used my increasing decreasing chart for the second derivative, and I have a sign change around each one of those, so I have 2 inflection points. So using my derivative speak, since f double prime of x is greater than 0 on negative infinity to -1, and f double prime of x is less than 0 on -1 to 0, the point -1, -3 is an inflection point. Since f double prime of x is less than 0 on -1 to 0, and f double prime of x is greater than 0 on 0 to infinity, the point 0, 0 is an inflection point. I do not have a vertical asymptote because it's a polynomial. I also do not have a horizontal asymptote because it's a polynomial. My end behavior is up, up, and I know that because I have a positive leading coefficient and an even degree. So that's how I come up with my graph. Here is my relative minimum, here's an inflection point, and my other intercept. Next one. Again, go through, find all the answers to this, unpause when you're ready to check your work. Alright, so this one's a little bit more work, but here's what our graph should look like in the end. We've got some asymptotes, slant and vertical going on, maximums and minimums. So let's go back up to the top and figure out this stuff. So, domain. Set the denominator equal to 0, negative infinity to 2, 2 to infinity is our domain. Now, before we do that though, remember we want to see does the numerator factor and does something cancel? Now, if it cancels, then it's a whole and not an asymptote, so it's still not part of the domain, but it's still something we want to check. In this case, that does not happen. So here, I could see that the numerator did not factor, so I tried to solve it by completing the square, and I stopped as soon as I realized that I was going to get a negative value, which means I would have complex solutions. So that leads me to no x-intercepts. The range. So the range, although it is at the top of the page, we're not going to be able to get the range until we figure out the maximums and minimums. The range comes out to be negative infinity to -2 with a bracket on the -2, and then 6 to infinity with a bracket on the 6. And those, the -2 and the positive 6, those are y values of the maximum and minimums. There is no symmetry. We can see that visually once we actually do the graph. But you could also do our test for symmetry about the x-axis and the y-axis. I'm sorry, about the y-axis and the origin. But in this case, it's pretty obvious once we do the graph that there is no symmetry. So again, these two things here, I would actually wait to do until the end, although they're put at the top of the page. Okay, so back to here, we talked about why we have no x-intercepts. The y-intercept is 0, -2. Now for the derivatives. They come out to be pretty nice, but there's a little bit more work involved. So we have to use the quotient rule. So I do bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. I want to simplify this. And it simplifies pretty nicely into x squared minus 4x over x minus 2 quantity squared. Second derivative, have to use the quotient rule again. So bottom times the derivative of the top minus the top times the derivative of the bottom, so here I had to use the chain rule, over the bottom squared. Now here to simplify, notice that you have an x minus 2, an x minus 2 squared, and an x minus 2 to the 4th in the denominator. So I factored out an x minus 2 in the numerator and then reduced the denominator. That made simplifying the numerator much easier. So when I do this, I end up with 2x squared minus 8x plus 8 minus 2x squared plus 8x. The 2x squared, the negative 2x squared, the negative 8x, and the 8x all reduce, and I'm left with just 8 over the quantity x minus 2 cubed. So it's pretty nice in the end, but it was a little bit more work to get to it. Alright, now my critical values. So I set the numerator of the derivative equal to 0, and I set the denominator of the derivative equal to 0. The numerator gives me x equals 0 and x equals 4. The denominator gives me x equals 2. So these are my critical values, but I do want to note that, that x equals 2 is not in my domain. So I know that that is not going to be a maximum or a minimum. However, I still need to use it in my increasing and decreasing chart. So I still want to put it in there, just to look and notice any possible sign changes. It's not going to be a maximum or minimum, but it still can give me information. So I create my increasing and decreasing chart. Let me rephrase that. It's not that the 2 is giving me information, it's helping me not make a mistake, because there could be a sign change here still, even though it's not a maximum or minimum. And if I don't put it in there and restrict this interval to 2 to 4 and this one to 0 to 2, I could mess up. If I just went 0 to 4, I might just end up with a positive in here, because part of it might be positive, and that could mess up my answer. So still keep that critical value in your increasing and decreasing chart, even though I know it's not going to give me a maximum or a minimum, even if those did create a sign change. Okay, so I see that I get a maximum and a minimum. So since f prime of x is greater than 0 on negative infinity to 0, and f prime of x is less than 0 on 0 to 2, the point 0, negative 2 is a relative maximum. Since f prime of x is less than 0 on 2 to 4, and f prime of x is greater than 0 on 4 to infinity, the point 46 is a relative minimum. Possible points of inflection. Set the numerator of the second derivative equal to 0. 0 does not equal 8, so that doesn't do anything for me. Set the denominator of the second derivative equal to 0, and I get x equals 2. So this is my possible point of inflection, but again, that is not within the domain of the function, therefore I know it's not going to be an inflection point. And at this point we've probably figured out it's a vertical asymptote, but I do still want to do that the concavity chart for the second derivative, because although 2 is not going to be an inflection point, it still tells me the concavity to the left of that and to the right of that. So that can be useful information. So there is a change in concavity, but it is not an inflection point. So for inflection point we put none. Vertical asymptote is at x equals 2. There is no horizontal asymptote, but there is an oblique asymptote. It is the slant asymptote y equals x. I got that by doing synthetic division. And so then I can come up with my graph. So I graph my slant asymptote, I graph my vertical asymptote, I graph my maximum, my relative maximum, which happens to be my y-intercept, and I graph my relative minimum. And so now I can see from the graph how I came up with those intervals for the range, and I can easily see that it does not have any symmetry. Alright, last one. Pause the video, unpause when you're ready to check your work. Alright, so this one should look like this, where we have 2 horizontal asymptotes and an inflection point. There are no maximums and minimums, or minimums. So how do we get that? Well, first we recognize the domain is all real numbers, because the numerator, I can plug in anything, and the denominator, no matter what I plug in, that's going to be a positive value. The range is negative 1 to 1. Again, I'm going to get that at the end. The symmetry here, I can do my algebraic tests for symmetry, and I can see that negative f of x is the same as f of negative x. Therefore, this is going to have symmetry about the origin. Again, that might be easier to recognize once I do the graph. The x-intercept is going to be the point 0, 0. The y-intercept is also the point 0, 0. First derivative is a little bit of work, but then simplifies nicely again. So again, I use the quotient rule. So bottom times the derivative of the top minus the top times the derivative of the bottom, where I have to use the chain rule, over the bottom squared. Now when I start to simplify, I end up with the square root of x squared plus 2 minus x squared over the square root of x squared plus 2 over x squared plus 2. So I multiplied the numerator and denominator by the square root of x plus 2. By the square root of x squared plus 2. So when I do that, this term here just becomes x squared plus 2. The second term in the numerator, the denominators cancel, and I'm left with just minus x squared. And in the denominator, I just have this quantity down here, which simplifies nicely into 2 over the quantity square root of x squared plus 2 cubed. The second derivative then is much easier. I can rewrite the first derivative. Remember, do not use the quotient rule in this scenario. Since this is just a constant, I bring that in front, and I think of this as x squared plus 2 to the negative 3 halves. So I do the chain rule with that. I get 2 from this 2, and then bring down the negative 3 halves times x squared plus 2 to the negative 5 halves times the derivative of the inside, which is 2x. And now I can simplify this, and the second derivative is negative 6x over the square root of x squared plus 5 to the 5th. Alright, I'm going to stop this video here because we're running out of time, so go on to part 2 and we'll talk about the critical values and the inflection points and how we come up with the graph.